Today, I will be discussing about the secure hash algorithm 256, which is one of the cryptographic hash functions used in the society today. More specifically, I will delve into the following topics: the use of SHA-256 in cryptocurrency, its brief history, overview of how it works, its properties, algorithm, and then finally, its other applications. So what exactly is a cryptographic hash function? To provide a background for better understanding, I will first talk about Bitcoin, which is actually recently gaining more popularity here in the Philippines. Bitcoin is a decentralized digital currency. It is a type of money that is completely virtual and is regarded as decentralized because it can be bought, sold, or exchanged without an intermediary such as a government or a banking institution. This is why it is said to operate under a peer-to-peer system where individuals can make transactions directly with each other. However, without a central governing authority, how can these individuals prove their transactions? How can we be sure that they actually paid for something? Or better yet, how can we even know that they had the money at all? This problem is called the double spending problem. It is the risk of digital currency being spent more than once. Being completely virtual, this form of money makes it possible for people, especially those with the knowledge and computing power, to simply produce copies of their digital money and spend it for multiple times. This is avoidable with traditional physical currencies because this type of money cannot easily be replicated. Furthermore, people have a more evident way of proving its authenticity and its past ownership. However, this is not the case with regards to virtual currencies. Fortunately, the creator of Bitcoin under the name Satoshi Nakamoto devised a solution in October 2008 called the proof of work. So what is proof of work and how does it work? Proof of work is a consensus algorithm that is used by Bitcoin and other cryptocurrencies to verify transactions. In order to explain how this is applied, I first need to introduce the concept of a blockchain. So, Bitcoin is built on what we call the blockchain technology, which is a public ledger that contains the history of every Bitcoin transaction that ever occurred. It is composed of a series of blocks, each containing the following: data about previous transactions, a cryptographic hash of the block that it extends or the hash of the previous transaction, and a timestamp showing the time of the block's creation. So how is the blockchain related to the proof of work? Well, before a block can be added to the blockchain, it must first have a valid proof of work, which can only be achieved by solving cryptographic problems. This activity is called Bitcoin mining, and the people who perform this are called miners. Any network participant can be a miner, and the miner who generates a valid proof of work first will be given a free Bitcoin as a reward and compensation for the computing power that he or she spent. However, it must be noted that only those with very strong computing power are likely to solve these highly complex cryptographic problems, especially with the conception of large Bitcoin mining farms. With expensive and fast computing resources, mining has become more and more challenging and costly. But what are these cryptographic problems anyway? In order to find a valid block, a miner is tasked to generate a hash that satisfies the specific condition provided by the network protocol. He or she must hash three things: the hash of the previous block, the data of the set of transactions that will be added to the blockchain, and a nonce, which is short for number only used once. This nonce is repeatedly incremented in the block until its value gives the block's hash the required number of 0 bits that are specified by the network protocol, also known as the target. The particular hash function used by Bitcoin is known as SHA-256. SHA or SHA stands for Secure Hash Algorithm, and the 256 simply means that it outputs a 256-bit long string. SHA-256 is actually just one type under the SHA family of hash functions, which was first introduced in 1993 by the National Security Agency with SHA-0. After 2 years, the National Institute of Standards and Technology developed the SHA-1 to fix the security issues found in its predecessor. However, weaknesses were still found in SHA-1, which led to the creation of the SHA-2 family in 2001. It is called a family because it consists of a total of 6 hash functions, each with different digests or hash values, or in layman's term, sizes, which are indicated in their numbers. So, SHA-224 is 224-bit long, SHA-256 is 256-bit long, and so on. SHA-512/224 and SHA-512/256 are just truncated versions of the others. So, how is the SHA-2 more secure compared to its predecessors? In order to answer that, I will first give a brief overview of how the secure hash algorithm works. In this presentation, I will focus on SHA-256 primarily because it is the most widely used type in authentication protocols and is actually the one employed by Bitcoin, which I have discussed earlier. So how does the secure hash algorithm work? SHA takes an input of variable length and always converts that into an output of fixed length. The message size or the size limit of the input and the message digest size or the length of the output, aka the hash value, both depends on the type of SHA. In the case of SHA-256, it can take an input of any length between 0 and 2 raised to 64 and will always generate a hash value that is 256-bit long. A single character, a word, a sentence, a paragraph, or even an entire book as input will have the same length of hash, which is 256-bit long. It converts data into an alphanumeric hash in hexadecimal representation, meaning its hash value is composed of a total of 64 characters that are either letters or numbers. You may be wondering why the number of characters is 64. Well, 1 byte is equal to 8 bits, and one character in hex can be represented using a total of 4 bits. Since the hash value is 256-bit long, 256 divided by 4 bits per character results to a total of 64 characters. The secure hash algorithm is considered as a secure cryptographic hash function because of its following properties. Number 1, it is deterministic, meaning it will always produce the same hash or the same set of 64 alphanumeric characters for the same input. This is important because if the results differed every time, then we will have no way of keeping track of the input data that we hashed. Number 2, it is quick to compute. SHA is not a form of encryption. It is designed to be more of an authentication method and not as an encryption that must be decoded, which leads me to its third property, which is pre-image resistance. Pre-image resistance means that it is infeasible to determine the original input data from the output hash. I use the word infeasible because determining the input is not entirely impossible, since the hash generated for a particular input will always be the same. However, since the only way to determine the input is by brute force or trying every possible combination of the input data, then this threat becomes insignificant. The fourth property is the avalanche effect. This means that a slight change, even just changing a character from lowercase to uppercase, and vice versa, will completely change the resulting hash. This property makes the hash pre-image resistant. Finally, SHA's fifth property is its resistance to collision. Collision is when two unique inputs have the same hash value. As I've mentioned earlier, the size limit of the input value for the SHA-256 function is 2 raised to 64, which is infinitely large. This means that almost anything can be hashed using SHA-256, and all of these things, regardless of their size, will all be converted to a 256-bit string. So how is it possible for every hash output to be unique? Well, the answer to that is no, it is not possible. In fact, no hash function is completely collision-free. However, like the explanation that I provided for the pre-image resistance, it is highly unlikely to find two input values that will yield the same hash value. It will simply take too long, which makes it an insignificant threat. Going back to my question earlier, how is the SHA-2 more secure compared to its predecessors? This is because SHA-0 and SHA-1 both produce only 160-bit long hashes. Having a shorter length, the hash values that they produce have lower number of different combinations, which makes them more susceptible to collision. Now that we've gained a deeper understanding of what SHA-256 is, let's dive into the mathematics behind it. The hashing algorithm might be overwhelming for a lot of us, so I divided my explanation into 6 parts to make it more digestible. For the first part, let's discuss some of the terminologies that we will encounter. Number 1. Bit is a binary digit that has a value of either 0 or 1. Number 2. Byte is a group of 8 bits. Number 3. A word is a group of 32 bits or 4 bytes, since 32 divided by 8 is equal to 4. Number 4. Hexadecimal notation is the number system of base 16. Finally, a hex digit is, as I've discussed previously, a representation of a 4-bit string. This may be confusing, so let's have an example. Suppose we have the decimal number 26. Decimal meaning the number is of base 10, which is basically the number system that we all use in everyday life. Let's first convert it into a binary digit. As mentioned earlier, a bit can only have the value of either 1 or 0. So in converting the number 26, we have to divide it continuously by 2. Then we get the remainder after every division. After which we get all the remainders from the bottom to top, and that's our resulting binary number. We can check if this is correct by converting the resulting 5 bits we got into its decimal equivalent. To do this, we first list the binary digits, after which we write the powers of 2 since we are converting from the binary number system which is of base 2. I'll only write until 2 raised to 4 since we only have 5 bits, after which we multiply the digits by the powers of 2, and then we get the sum of these products. So there, we got our decimal number 26 back. Now, in converting this 5-bit string into hexadecimal, we have to add an extra step at the start, and that is, we must first group the bits into 4, starting from the least significant bit, which is the one on the right. Why so? Because as mentioned earlier, one hex digit represents 4 bits. So if the grouping does not have enough to form 4 bits, then we can simply add zeros before the most significant bit or the bit at the leftmost part. Now, we simply have to multiply the digits by their corresponding powers of 2 as shown earlier. Note that 10 is represented in hexadecimal notation as the letter A. So we simply append these two values together, and there we have the decimal number 26 in hexadecimal notation. We can recheck by converting this to binary. To do this, we just have to convert each hexadecimal digit into 4 binary digits. We can do this by first writing down the powers of 2 and then see which products, when added together, will give us a sum equivalent to the hex digit. We see that 2 raised to 3 plus 2 raised to 1 is equal to 10 and 2 raised to 0 is equal to 1. Then we simply concatenate these together. We can just remove the leading zeros and our resulting binary digit already looks exactly the same as the one we had before the conversion. Now that we're done with the basic terminologies, let's head on to the operations that will be done on the words or the 32-bit strings. Before anything else, I want you to know that I will be using 4-bit strings as examples, but it is important to take note that SHA-256 operates on 32-bit words. I'll just use smaller numbers for your easier and better understanding. Okay, so for our first operation, we have the exclusive or logical operation, which results to a value of true or 1 if the operands have different values and false or 0 otherwise. The XOR operation is used to give a balanced representation of its different operands. The second operation is the right shift operation denoted by this symbol. This simply shifts the bits of the 32-bit word to n number of positions to the right. So for our first example, the n is 1. So we just have to move every digit to the right, giving us 0, 1, 0, 1. In the next example, our n is 3. So we just move each of the digits to the right for a total number of 3 times. Giving us 0, 0, 0, 1. The third operation is the rotation right, which also moves the digits of the 32-bit word by n number of positions to the right. So how is this different with the previous operation? As we move the bits to the right, the 1 at the end is stored back at the leftmost digit of the word instead of disappearing completely, unlike in the shift right operation, which is why it is also known as the circular right shift operation. The fourth and last operation is the addition modulo 2 raised to 32. This is done by first adding the integer equivalent of the binary words together, then getting the remainder when this sum is divided by 2 raised to 32. Afterwards, we just simply convert the remainder, which is an integer, into a binary word. Note that this operation can be done directly using the binary words by following the rules of the operations in terms of the binary system. But for simplicity, I will convert the words into integers and just convert it back to binary once we already have the final value. but the results in either cases should be the same. So why do we have to take modulo 2 raised to 32 after addition? This is so that the number of bits of the result would be constrained to 32 bits. To illustrate, we know that modulo returns the remainder, right? So for example, we need to generate a number that can never be larger than 9. What we can do is take the modulo of that number by 10. For instance, the number is 15. 15 modulo 10 is 5, which is less than 9. 1199 modulo 10 is 9, which is still not greater than 9. 32-bit words are very large, already in the range of billions, so I will just use a smaller number as an example. In that case, I will change the 2 raised to 32 divisor in order for you to properly see the effect. So for example, I will add the decimal numbers 100 and 200 together, and when converted to binary digits, I want to have a number that will not exceed the length of 7 bits. Since our first bit starts with 2 raised to 0 and our 7th bit is at 2 raised to 6, I will use 2 raised to 7 as my divisor. So in adding the two numbers, we have 300 and then 2 raised to 7 can be simplified as 128. Then we just take the modulus operation by dividing the 2 and getting the remainder, which is equal to 44 of base 10. This is converted to binary as 101100. We can prove that this is equal to when we directly use binary. I already converted the numbers into binary beforehand, but you can try it on your own. Just apply the conversion from decimal to binary that we've learned earlier. So, converting this binary number to decimal, we are able to get the decimal number 44 back. Now that we're done with the operations, let's discuss the 6 logical functions used by SHA-256. First is the lowercase sigma 0 function, which takes one 32-bit word, performs the rotate right on that word for 7 and 18 number of positions, and the shift right operation for 3 positions, and then XORs each of the results together. The next 3 functions all operate the same as the first one, except that the number of positions of every operation in each function is different. For lowercase sigma 1, it takes a single 32-bit word, rotates right by 17 and 19 positions, and shifts right by 10, and then XORs the results together. For uppercase sigma 0, it also takes a 32-bit word and also rotates right, but for 2, 13, and 22 number of positions each, and then XORs each of the results together. For uppercase sigma 1, on the other hand, it also takes a 32-bit word and also performs the rotate right operation, but for 6, 11, and 25 number of positions each, and then XORs the results together. As you may have observed, the only difference between the lowercase and uppercase sigma functions is that the lowercase sigma function uses the shift right operation while the uppercase sigma function does not. There are 2 other SHA-256 functions, but unlike the previous functions, these ones do not make use of the rotate and shift right operations. One is the choice function denoted by CH, which takes 3 32-bit word inputs x, y, and z. It is defined in terms of a logical statement as ANDing x and y and not x and z respectively, and then performing the XOR operation on these 2 bits. However, there is a simpler way of interpreting this function. Every bit in the result depends on the value of the bit at that particular place. If the bit in x has a value of 1, the resulting bit will be whatever value is in y. Else, if the value in x is 0, the result would take the value of z at that place. The last function is called the majority function denoted by maj. It also takes 3 32-bit word inputs. As a logical statement, it is performed by ANDing x and y z, and y and z separately, and then performing the XOR operations on these 3 results. However, there is also an easier way to interpret this function. From the name itself, what it simply does is that it takes the bit that appears most frequent among the 3 bits in every place of the 3 inputs. Now that we're done discussing the functions, I'll just show the different constants that will be used in the hashing process. SHA-256 uses a sequence of 64 constant 32-bit words denoted by k sub 0 to k sub 63. So where do the values come from? all of the constants take the first 32 bits of the fractional parts of the cube roots of the first 64 prime numbers. The fractional parts of the cube roots of prime numbers give random-looking bits, which makes them a good source for a constant that can mix up the message being hashed. Now that we've covered pretty much everything needed to understand the hashing process, let's finally delve into the actual hash algorithm of the SHA-256. I will discuss this in two parts, again to aid your comprehension. So, the first part is the pre-processing or the processes that we must first do with our input before the computation begins. In pre-processing, there are 4 steps. The first thing we have to do is convert our message into binary. How so? There is what we call the American Standard Code for Information Interchange, or simply the ASCII code, which assigns one particular value for every character. So, using this, we just simply get the number assigned to each character in the message and correspondingly convert it into binary. So, say for example, we have the input ABC. Based on the ASCII table, A is equal to 97, B is 98, and C is 99. Converting these numbers to binary, we have the following bit string. After we have represented our message in binary, we are now at the second step, which is expanding the number of bits in our message to the nearest multiple of 512, since the SHA-256 hashes data in chunks of 512 bits. How are we going to increase the number of bits to 512, you may ask? It's simple. We will just add zeros to the message. But before we do that, we will first have to append a 1 at the end of the message to serve as a separator between the actual message and the trailing zeros that are just padded for expansion. After appending a 1 at the end, we will have to start padding the message with zeros. Exactly how many zeros are we supposed to add? Let's look at the formula here where L is the length of the message or the total number of bits of the message, and K is the number of 0 bits that we will pad. So L plus 1 plus K is congruent to 448 modulo 512. It might seem intimidating, but what it only means is that we will have to add K number of zeros such that the total number of bits of the message plus 1 bit because of the separator we added earlier plus the number of zeros that we will add will have a remainder of 448 when divided by 512. So, counting the total number of bits of our actual message, ABC, its length is 24 bits. Then we convert the number 24, which is again the length of the actual message, into its binary equivalent, which gives us 1100. If the resulting length is less than 64 bits long, we simply have to add 0 starting from the left of it to make it 64 bits long. And then just append this to our 448 string previously. And there we have a 512-bit string, which is what we call a message block. Please do take note that we can have more than one message block, each containing 512 bits each. This is possible when we have an actual message that is already more than 512 bits long. In that case, we will have to pad zeros until its number of digits reaches the next nearest multiple of 512, such as 1024 and so on. But in our case, since our input, ABC, is just short, we only have one message block. Nonetheless, the operations done on each message block is just the same. Hence, what I'll be doing next for our one message block will just have to be repeated for the other blocks, if any. Okay, so moving on, we are now at the third step, which is parsing the padded message. What we simply have to do here is split our 512-bit message block into 16 32-bit words, which collectively is called the message schedule. So why 16? Because 512 bits divided by 32 bits is 16. However, SHA-256 requires a message schedule with a total of 64 32-bit words, and we only have 16 as of now. This means that we have to create 48 more words, and to do that, we will be using the already existing 16 words and the formula shown below. This might seem complicated, but it is not. We just have to apply what we learned earlier in order to get the next terms. For example, the lowercase sigma 1 here is just the function that we discussed previously, which does 3 operations to a word, namely rotate right by 7, rotate right by 18, and shift right by 3. And finally, XORs these 3 resulting values together. The t-2 here means that the input for the lowercase sigma 1 function is the term that is 2 units before the current term being computed. Let's look at the example for better understanding. For example, getting the 17th word, we have t equals 16 since we started at index 0. To get its value, we simply have to do the lowercase sigma 1 function to the term at 17 minus 2, which is t equals 15, or simply the term ahead of it by 2 places. Then we simply take the value at t minus 7, which is at t equals 10 in this case. We don't have to perform any function for this as stated in the formula. Next, we get the term 15 places before the term being generated, and perform the lowercase sigma 0 function on the value. Recall that the lowercase sigma 0 function takes an input, performs rotate right by 17, rotate right by 19, and shift right by 10, and then XORs the results together. Then, we simply get the value 16 places before the 17th word, which is at 16 minus 16 or t equals 0. Finally, after getting the 4 values, we just perform the addition modulo 2 raised to 32 operation that we discussed earlier, which is adding the values together and takes modulo 2 raised to 32 to constrain the number of bits to 32 bits. This formula will be used for every succeeding words at t equals 17, 18, 19, and so on until we reach t equals 63, which means we already have 64 words in our message schedule. Now that we've prepared our message schedule, we are finally at the last step of the pre-processing, which is setting the initial hash values. We have to initialize a total of 8 hash values. The values of each is taken from the first 32 bits of the fractional parts of the square roots of the first 8 prime numbers in binary notation. I know that you may be overwhelmed by all of the information we have discussed, but hang in there because we are finally at the second and last part of the hashing algorithm. This part has 4 steps, but we already did the first one earlier, which is the preparation of the message schedule. So now we will head on to step number 2. Step 2 is initializing what we call the 8 working variables, which are the 8 slots where the words will fall into later on. These are signified by letters A to H, and are initialized using the 8 initial hash values I've shown earlier. Step 3, we will now be doing the compression function where we are going to modify the values stored in each working variable using the values in our message schedule, which is denoted by W sub t. Note that the process that I'm about to show will be done to all 64 words in the message schedule, hence the t equals 0 to 63. So in this process, we will be needing 2 temporary words, t sub 1 and t sub 2, each with a corresponding formula that will be using the words, constants, and working variables as inputs. This may seem overwhelming, but don't worry because I will explain it one by one. Let's start with t sub 1. The formula simply means that we have to take the working variable h, the uppercase sigma 1 of e, the choice of the working variables e, f, and g. We also need to take one word in the message schedule denoted by w sub t and its corresponding constant k sub t. Afterwards, we simply have to add all the 5 values together. And don't forget to take the sum modulo 2 raised to 32. Remember that we always perform the modulus operation after getting the sum to contain the number of digits to 32 bits. To illustrate, let's look at this. Since we are just starting, we get the first word w sub 0 and the first constant k sub 0. Next, we get the choice of e, f, and g. Then we get the uppercase sigma 1 of e, which is rotate right by 6, 11, and 25, then XOR them together. Then we get h and finally add these 3 values with w sub 0 and k sub 0. We now head on to t sub 2, which is simpler. For the first value in the equation, we just have to perform the uppercase sigma 0 on a. Then we just perform the majority operation on the working variables a, b, and c to get the second value. Finally, we perform the addition modulo 2 raised to 32 operation on the 2 values, and there we have our second temporary word. So again, we must first take the majority of a, b, and c. Then we perform the uppercase sigma 0 function to a by rotating right by 2, 13, and 22, then XOR them. Finally, we just add the 2 values together. After obtaining the 2 temporary words, we now update our working variables. The first thing we should do is move all of the values of our working variables by 1. So we store the value of a working variable to the next variable and lose the last one since there is no variable after it. And then we put a new word into a, which is the sum of t sub 1 and t sub 2, or the value obtained when we add the values in t sub 1 and t sub 2 and take modulo 2 raised to 32 of the value afterwards. We also have to add t sub 1 into e. So this process repeats until we have done it for every single word and constant, Remember that we have 64 words in our message schedule with corresponding 64 constants. Hence, we have to perform the compression on each of these words for a total of 64 times. Step number 4. We have to take the initial hash values that we started with and add the end result of our compression to each hash value. And then we're done with the compression of our first message block. Remember that we did this process only once since we only have one message block. But in the case where we have larger inputs that will generate more than one message block, we will have to do step 5, which is performing the said process for each block, each using the intermediate hash values that were generated in the previous blocks. This will be done until every message block is compressed into our hash values. Finally, we are now at the final step of the algorithm. Once all of the blocks are compressed, the final hash values are each converted into their hexadecimal representation and finally concatenated together to form the final message digest that is 256-bit long, or 64 characters long in hexadecimal representation. Remember that we have 8 hash values times 32 bits is equal to 256 bits, which confirms that the final message digest has a total of 256 bits. And there you have it! We finally converted our input ABC into a hash value using SHA-256. SHA-256 is commonly used in validating software that are downloaded from websites. It is also used in logging onto various operating systems such as Unix, and is also applied by companies when storing their users' passwords. When a user enters a password, the password usually runs through a hash algorithm, and the output hash value is compared to the company's user database. SHA-256 is also used in preventing software piracy and detecting unauthorized file modification such as web page defacement, signing database keys, system file modification, virus signature update, and so on. With its vital role in authentication and security, a lot of us may have thought that SHA-256 is a highly complex algorithm that normal people cannot understand. But as we dissected the algorithm into smaller steps, we were able to learn that SHA-256 is not that complicated after all. What lies behind it is not some sort of mystery, but basic mathematical concepts and operations that we already know. Similar to this, there are a lot of other things in the world that may seem very complex, but one must only know how to break down the problem into simpler and smaller problems. Then one can certainly understand anything. I hope you all learned something today. Thank you for watching!